Hello everyone, welcome back to another video in our AI deep learning machine learning series. My name is Dean, and today we'll be covering a deep dive into LLMs. So this video is heavily based on Andrej Karpathy's video regarding the topic, so I have that link down in the description. But without further ado, let's begin. So first up, I have an example of a prompt given to both ChatGPT 3 and also InstructGPT. So the prompt asks to explain the moon landing to a 6-year-old in a few sentences. So GPT's 3's response is, instead of sticking to the specific request to explain the moon landing, GPT-3 starts providing unrelated scientific concepts like gravity, relativity, and the Big Bang Theory. These are all valid scientific topics, but don't directly address the simplicity or context of explaining the moon landing to a young child. It shows that GPT-3 might struggle to understand or follow the exact intent of an instruction, especially when the task requires simplifying complex ideas for a specific audience, like a 6-year-old. So, InstructGPT, however, does exactly what the prompt asks for. It provides a very simple, straightforward explanation. In the example here, you can see people went to the moon and they took pictures of what they saw and sent them back to the Earth so we could all see them. This is the ideal response because it is simple and appropriate for a 6-year-old. It also focuses on the core idea of the moon landing without overloading someone with technical details, and it also directly aligns with the request to explain it in a few sentences. So, InstructGPT is specifically fine tuned to follow instructions more precisely and to generate responses that are actually contextually appropriate based on the user's input. It understands not just the content of the request, in this case the moon landing, but also the style and tone. So in this case, it'd be simple enough for a young child to understand. GPT-3, while it's capable of generating coherent responses, it tends to veer off the track of if it doesn't clearly understand specific details of the prompt, or if the request invokes certain tasks like adjusting complexity or tone for a certain audience. With that said, let's talk about something called pre-training. So, before a language model like ChatGPT can be useful, it has to learn how to generate text that resembles human conversation. This is done by training the model on vast amounts of text from the internet, so everything from books and articles to websites and forums. During this phase, the model is basically trying to predict the next word in a sentence. For example, if the model is given the phrase, the cat sat on the blank, it would try to predict the next word because based on what it's learned so far. But while the pre-training allows the model to mimic human language, it doesn't make it capable of having a true conversation. This is where post-training comes in. After pre-training, the model undergoes a secondary training process where it learns to behave more like an assistant. This stage is less computationally expensive than pre-training, and it focuses on helping the model engage in multi-turn conversations. It's essentially what allows the model to carry on a back and forth dialogue, rather than just spewing out random context. Now, the post-training phase wouldn't be as effective without human help. This is where human laborers play a crucial role. These people create data sets of ideal responses for the model to learn from. Essentially, they teach the models how to act as a helpful assistant, which includes understanding how to respond to questions, refusals, and even how to politely say, I don't know, when the model doesn't have an answer. They also make sure the model learns how to be polite and safe in its responses. Human labeling is more than just giving the model a list of correct answers. It's about structuring conversations in a way that makes sense to the model. Special tokens are used to differentiate between user input and assistant responses, helping the model understand the flow of a conversation. These tokens guide the model's learning process, allowing it to generate better, more context aware responses. But here's the little secret: while the model might seem pretty smart, it's not perfect. Sometimes it can generate information that's just plain wrong. We call this phenomenon hallucinations. So these are the times when the model makes things up, often because it doesn't truly know the information or it's trying to generate an answer based on patterns rather than factual knowledge. So, how do we deal with this? One of the ways to handle hallucinations is to train the model to say, I don't know, when it's unsure about something. This can be achieved by showing the model examples of when it's okay to admit uncertainty instead of making something up. But even with this approach, the model can still get things wrong. So another strategy is to give it the ability to search the web when it's uncertain. When the model isn't sure about something, it can trigger a web search, grab the latest information, and update its knowledge. This process mimics how humans look up when they don't remember something off the top of their heads. Now, here's something interesting to know about language models. They don't have a quote unquote sense of self. If you ask a model like ChatGPT, who built you, or what model are you, its answers might not always make sense. That's because the model doesn't have memory of past conversations or an ongoing identity. Every time you interact with it, it starts fresh. The reason for this is that language models operate probabilistically, meaning they generate responses based on patterns they've learned. But they don't actually understand the content in the way humans do. This is why sometimes they give answers that sound plausible but are completely wrong. It's like a random guess based on previous patterns, not a definitive answer. This is why also why you may see them making simple mistakes, like math errors or saying that 9.11 is greater than 9.9. Despite being trained on tons of data, the model struggles with even basic arithmetic at times. Speaking of math, let's take a moment to talk about one of the biggest challenges language models face: solving math problems. You might think that an AI could easily handle simple calculation, but in reality, the model struggles with anything beyond basic arithmetic. This is because the model processes one token at a time, and complex problems require more tokens to break down and solve properly. For example, if you ask the model to solve a large math problem in one step, it might fail. To fix this, we can guide the model to work through problems step by step, breaking them into manageable parts, or we can use Python code to verify the results. For prompting the model to generate code, we can leverage its ability to execute the code in a real interpreter, which is far more reliable for solving math problems than the model's internal mechanisms. Now that we've covered the basics of training and challenges the model faces, let's talk about reinforced learning, RL for short, the final stage of training. Think of it as the model practicing problem solving. Reinforcement learning is similar to how humans learn in school. First, you gather information, which we can call pre training. Then you learn by imitating experts, which we can call supervised fine tuning. And finally, you practice by solving problems and getting feedback, which we can call reinforcement learning. In reinforcement learning, the model generates multiple solutions for a given problem and receives feedback on which ones are correct. The correct solutions are reinforced, meaning the model will be more likely to use the same approach next time. This iterative process helps the model refine its responses over time, learning from its successors and mistakes. There's also an interesting distinction in AI training between verifiable and unverifiable domains. In verifiable domains like math or factual questions, we can easily check if the answer is right or wrong. But in unverifiable domains like creative writing or humor, it's much harder to judge correctness because there's no truly right answer. That's where reinforcement learning from human feedback, or what we call RLHF, comes in. Instead of having humans manually score each response, they rank multiple generated answers, and the model learns from those rankings. Over time, the model gets better at understanding human preferences, especially in creative tasks. RLHF is a powerful tool for improving models, particularly in domains when there's no single correct answer. It makes reinforcement learning scalable and helps models generate more human like responses. However, like all tools, RLHF has its drawbacks. The reward model can sometimes be inaccurate, and if you use too much, it can lead the model to game the system, as we call it, which it just makes it so that optimizing for feedback, it just makes it so the AI optimizes for feedback loops rather than actual human preferences. This is why RLHF needs to be managed carefully. If you run it too long, the model might start producing nonsensical answers or optimizing for artifacts in the training data rather than useful real world outcomes. And that's basically a wrap for today. So we've covered everything from the basics of pre-training and post-training to the challenges of hallucinations and how reinforcement learning fine-tunes these models into the powerful tools we use today. Hopefully this gives you a deeper understanding of how AI like ChatGPT works and why it's so impressive, and sometimes, a little quirky. So once again, my video is heavily based on Andrej Karpathy's video onto the topic. I'll have that link down in the description along with the moon landing example that I shared. That's all for me. Have a good day.